Hey, good morning, Mr. Jenkins. I'm Dr. J. How are you feeling?
I don't know why it's so hard for me to walk these days.
Yes, I spoke with your doctor. It seems like you have Parkinson's disease. I have just the right solution. Don't
Huh?
worry. I'm just kidding, Mr. Jenkins. But if you have some time, I'd
Oh,
love to tell you more about your
but
condition.
yes, of course, I would love to know more about Parkinson's disease.
Alright, so let's get started with a little bit of background information. Dopamine is a neurotransmitter and hormone that's commonly found in the brain. However, to be more specific, it is commonly produced in the ventral tegmental area, the substantia nigra, and hypothalamus. Dopamine is also known as the feel-good hormone. It can be categorized by its 2-hydroxyl group, its phenyl group, and amine group. Since dopamine is a part of our reward system, it's part of the reason why it feels so good to eat something sweet, such as chocolate cake, when exercising, or when we watch late-night movies. We already know that dopamine gives us a feeling of pleasure, but what isn't commonly known is that it plays a major role in movement and coordination. Dopamine works with our central nervous system by aiding in the transmission of signals to other nerve cells. Now, is all of this making sense so far?
Yes, but what does this have to do with my Parkinson's disease?
Don't worry, I'm going to explain that right now. In Parkinson's disease, something goes wrong in the brain. Researchers still do not know the exact cause of Parkinson's disease. However, there is a strong correlation between dopamine and Parkinson's. In a study done in 2015, researchers found that dopamine levels were abnormally low in people with Parkinson's. Here we can see the difference between a healthy neuron and a neuron that's affected by Parkinson's disease. We notice that there is a significant decrease in the amount of dopamine. As a result, this leads to movement disorders such as tremors.
Is there anything we can do to help me?
Yes, of course we can help you. This is where the medication Sinemet comes into play. It is a combination drug composing of carbidopa and levodopa. Together they work to help reduce the symptoms of Parkinson's disease. Here is an overview of how the medication works. First, in our body, we typically have L-tyrosine, which gets converted into L-dopa. The L-dopa is then converted into dopamine in our body. We'll further explain this in a few. L-tyrosine is typically obtained through our diet, and it acts as the precursor for L-dopa. It gets converted into L-dopa through the enzyme tyrosine hydroxylase. This process allows for the structure to gain a hydroxyl group and subsequently lose the carboxylic group when it gets converted into dopamine. So with the medication levodopa, we don't have to worry about the precursor as it's readily available and ready to convert into dopamine. It reacts with the enzyme DOPA-decarboxylase or DDC. DDC is a lyase enzyme that works with its cofactor pyridoxal phosphate, aka vitamin B6. Together they work to remove the carboxyl group through a process known as decarboxylation. As previously mentioned, pyridoxal phosphate, or PLP, is actually the active form of vitamin B6. This is why it's important to eat a healthy and balanced diet. It's important to notice its negatively charged structures. We'll take a look at that in a few. Alright, now it's time to examine the protein structures. Here, what looks like tangled up Christmas decorations is actually the ribbon diagram of the dopamine receptor. It is predominantly composed of several alpha helix structures, followed by beta sheets and extracellular loops. The receptor acts as a transmembrane protein to facilitate a pathway for dopamine molecules. To be more precise, it is a guanine nucleotide binding protein, or simply a G protein coupled receptor. G proteins mediate a pathway in response to hormones and neurotransmitters such as dopamine. Below the dopamine receptor, we can see that there are three subunits of G proteins: alpha in the blue, beta in the orange, and gamma in purple. Their roles are to aid in neurotransmission. Highlighted in red is the binding site of dopamine. Note that it is located within the plasma membrane. Here we can see some ionic bonding occurring between dopamine and serine 409, threonine 412, and aspartic acid 114. Once dopamine is binded within, it triggers a pathway down its subunits and allows the body to feel pleasure and optimal mobility. Now let's discuss the second part of the medication, carbidopa. It possesses a similar structure to levodopa, however it contains a methyl group instead of a hydrogen. and an additional amino group. These are key differences that will help us to understand why they are given together. Levodopa gets metabolized in the upper GI tract. Remember, DDC helps to convert levodopa into dopamine. However, not as much dopamine passes through the blood-brain barrier since it is too polar. In addition, this can also lead to some nasty side effects such as nausea and vomiting.
Yuck!
This is where the medication carbidopa comes into play. Carbidopa acts as a competitive inhibitor to DDC. As a result, it reduces the GI effects that DDC would cause and prevent L-DOPA from being converted into dopamine until it passes the blood-brain barrier. In other words, they form a dynamic duo to work together to help in the reuptake of dopamine.
Wow, just like me and you, Doc.
This big, beautiful blob, which may remind you of a pureed meal, is actually a surface representation of the enzyme DDC. Deep within, in the pink, is pyridoxal phosphate and carbidopa in blue. Here's the ribbon diagram version of DDC. Like levodopa, it is predominantly composed of several alpha helix structures, followed by beta sheets and extracellular loops. Highlighted here is the binding site of the cofactor and pyridoxal phosphate. It is kept bonded here due to ionic interactions occurring between it and, for example, asparagine 300 and lysine 303. In addition, there are several water molecules around, since PLP is a hydrophilic molecule. Highlighted here is the binding site of carbidopa. Here you can see some ionic bonding occurring between the hydroxyl groups in threonine 82 and isoleucine 101. Furthermore, there are a lot of water molecules in red, indicating its hydrophilic nature. Now, are you ready to take your medication?
You betcha. Wow, feels so much better. Whew, man. Thanks again.
Hey,
Doc.
wait!
See you later.
Oh, man. Yeah, it's me. Yeah, it happened again.